Welcome to Amber Book's 40 Minutes of Competence. I'm so glad you're here. The question this week is, in each of these four trusses, we want to identify which members are in compression, which ones are in tension, and we're going to assume that each one is under kind of a normal gravity uniform load, and each one is supported on its ends, even if I haven't drawn it as such. And so before we get to that, let's talk a little bit about the Scottish Parliament. Many of you guys know this building. It was designed by Ermann Morales. It was actually quite controversial. It's just now kind of getting its due among the Scottish populace, which at one point had voted at number 5 in buildings they'd like to tear down. It was not very popular when it first opened for all kinds of reasons. It was controversial because Thank you for wishing me happy birthday, Paige. I'm not quite sure how you knew it was my birthday, but I do remember mentioning it on one of the videos when I was talking about where the sun is. So yes, today is my birthday. So anyhow, I don't usually get distracted by the chats, but I was kind of freaked out when I saw happy birthday. I was like, how did she know? And then I remembered. Anyhow, the Scottish Parliament, this building was actually quite controversial for all kinds of reasons. One is, like, 300 years ago, the government of Scotland as an autonomous entity was dissolved, and it was incorporated into Great Britain, and all kind of parliamentary decisions were made down in London. In I think '97, Scotland had a referendum, and they wanted some more autonomy, and part of that was making its own parliament. And so for the first time in 300 years, they needed a building for Parliament. And because it's a modern Parliament, and because we like to have everyone in one room, and because we don't like to have columns, because we don't have to, in the middle of these big open spaces, we're going to have a roof that has a series of members that are in compression and tension, and we're going to use that to effectively increase the span of the building, and we're going to use it to effectively decrease the thickness of the beams of the building. In this particular case, we're also going to add a geometry that we probably wouldn't be able to pull off without all of these kind of tension members that you see here and here. And there's actually one that kind of goes along there somewhere that connects all of these V's, all these points together the other direction. Anyhow, it was supposed to be 10 to 40 million pounds. The budget wound up being 400 plus million pounds, so it went like 40x or 10x its original budget. That's a bit misleading because the original budget was based on kind of a bland office building. It wasn't really a budget based on a parliament building. It was based on kind of a generic office building. The total area of offices during construction doubled just because parliamentarians have a lot of power, and when they say, I want an office for my chief of staff, it's very difficult for anyone to say no. There was a series of multimedia facilities that were added, but it did go 3 years long on budget, and it was kind of a cautionary tale, or it was seen as a parable about government waste. It has since its construction or its completion about 15 years ago. It has since kind of come around. The architecture community always embraced it. It won the Sterling Prize, the RIBA Sterling Prize in 2005. Enrique Morales, you may know, died before its completion, but it was completed anyway without him, as it usually is the case. And the public has since come around to it, and it's actually starting to be a beloved symbol of Scottish autonomy. I just heard on my walk-in this afternoon, I just heard Scotland is one of 3 countries with Iceland and New Zealand that is redefining success from GDP growth to other measures like happiness GDP, or gross happiness product quotient, or something like that. So I don't know if Scotland would be able to even do that if they didn't have the kind of autonomous structure that this building was a part of the result of. Anyhow, this is our solution. We have, actually there should be a little tension element there, but we're going to go over those each individually. If you'd like to take a picture of these for your phone and look over them, you can, but you see it's compression, compression, tension, compression, compression, tension is down here, or tension is here and here. Tension, tension, compression, tension, tension, compression, compression, compression. These are tough. Tension, tension. That's the most difficult one. Most of these I think are pretty easy for architects. Generally, I think, here I'll put it back up. Generally, I think that in my experience teaching architecture, 3/4 or more of you kind of see it. You can just kind of look at it and see what's in compression and what's in tension. And I'll give you some tricks for figuring out when you can't see it, or if you can't see it. But generally, we can kind of see which things want to be squished down, and if left to their own devices, and which things want to be elongated if left to their own devices. This is the new, it's really a shame to get something good going like this and then change the time and the location. But we got something good going, and I'm going to change the time and location. It will go out to you in an email. But just be on the lookout that we're going to have our 40 minutes of competence going forward at this Zoom location. And you can always just punch in these numbers if you're having trouble with the link. And we're going to move it from what's now at 2 p.m. Eastern Time on Thursdays. We're going to move it to 6 p.m. Eastern Time on Thursdays. Why am I moving it? Well, as many of you know, I teach at Virginia Tech. I teach studio, and I don't know why I ever made it for 2 o'clock to begin with, because I had to know that studio was coming back. I don't think it really occurred to me when I did the first one that it would become a series, and so I made the first one at 2 and just kind of kept it that way. But anyhow, I'll put this up near the end of this session as well, so you guys can take another picture of it if you can't find your phone right now. All right, so this one is kind of a traditional gable truss, and so we have these supports at the end pushing back up. We have uniform gravity load kind of going along. And you should be able to kind of intuit that these things are going to want to push down and squish together. So generally, if we're describing something, a member that's in compression, we'll draw the arrows like this to demonstrate that it's in compression, that the forces from above are pushing against the forces from below. And of course, by the law of symmetry, it's going to be on the other side as well, but also by the law of common sense. And then this piece on the bottom is actually quite important. You probably know that it's pulling apart. And if you don't know that, just kind of picture it without it. If you didn't have it, this whole thing would kind of flatten down. So what starts as this would wind up pretty quickly. If you remove this thing right here, it would wind up pretty quickly to just be kind of flat. Or even, maybe it would even sag down. So this element here is holding it all together, and so we say it's in tension and we draw it like this. Now anytime we have the force, the weight, above an element like this, if this is a beam, if we're going to add what's called a compression strut, or just a strut. And a strut is one of those words that you likely have heard, but I think it's one of those words that you've heard so many times, some people are afraid to ask what a strut is. They've heard it in the context of vehicles, in car design, they've heard it in the context of structural design, but like a gusset plate or water table, those are kind of things that we hear a lot, and we just assume that other people assume we know what it is, and we might not know what it is. But a strut is just a short structural member that's in tension. And so if you were to support some kind of weight, you would put a strut here. And a strut has to be kind of rigid, like it has to be something with some thickness. You can imagine that it can't be something like a cable, because a cable would just flop down and the weight would just crash down on the beam. So if you see anything like this, it's a strut and it's going to be in compression. If you see anything like this, it's hanging. Well, that could be a structural element, like a piece of wood or a piece of steel, cold rolled steel or something like that. But it also could be, or any kind of steel really, but it also could be a cable or a thin rod. And the fact that it could be a cable or a thin rod and it would still work out, because we couldn't make this a thin rod because it would buckle. We couldn't make it a cable because it would collapse. But this, we can make a cable. You can imagine it just kind of swings that way. And So that element right there is in tension. I don't know of a word, the equivalent word for tension. Strut is to compression as blank is to tension. If you know, you can put it in the there's probably a word. You can put that in the chat, but we can just call it a tension rod. So we could put a tension rod there in the same way we could put a strut here. All right. Now, if we have just a straight up beam, you know that it's going to want to kind of, once we load it, it's going to want to sag like this. And what's going to happen is there's going to be a bending moment, and that bending moment is going to be at its max. If this is a simply supported, uniformly loaded beam, it's going to be at its max at the midpoint of the beam. And what's happening there in the beam is if the beam looks like this, and I know you guys know this, but if the beam looks like this, it's going to want to be in compression on the top. So in the top we have forces pushing together, and in the bottom we have forces pulling apart, and so it's going to want to split at the bottom, and it's going to want to kind of crush together at the top. And that's typically in like 99% of cases, the beam is going to be sized, 99% of the cases, the beam is going to be sized based on its maximum moment. But really what it's sized for is the maximum moment gets translated then into a maximum tension force internal to the beam that wants to split it apart at the bottom and the middle. And it also gets translated into a maximum compression at the top of the middle of the beam. And that's really what's going to dictate. So we say the moment dictates the beam, but in reality, it's the tension and the compression inside the beam that's caused by the bending moment that's gonna determine, it's gonna govern the thickness of the beam. So you can imagine that if we could somehow support that beam here, then our maximum moment becomes here and here, and that's a big difference because now our span is only this, and our maximum moment is based on the square of the length of the span. So if that's the length of the span, it's based on the square of the length. Just like originally our length was here, that length, and that is twice as long. Well, twice as long doesn't mean twice the moment because the square of 2 is 4. So actually twice as long of a beam, assuming all other conditions are held constant, it's uniformly loaded and simply supported, twice as long of a beam is going to be 4 times the maximum moment, which means 4 times the urge to rip apart at the bottom in the middle, and 4 times the urge to squish together in the top. So if we can cut the length of the free support, kind of the free body, the free beam, if we can cut that in half, we're actually not just cutting our moment in half, we're cutting it by a quarter, and we can span farther and or have a thinner beam. And that's what these two beams are about that you saw. So this one, you can see its in tension because it's a rod, so you can just tell that's in tension, and that's in tension, and that's a compressive strut. And what it is it's essentially like, think of it as a hammock. So you have this beam that's going to stretch from here to here, and its maximum moment is going to be right here in the middle. So what we're doing is we're building a hammock on the ends, and then we're going to put the whole thing in tension. We're going to use a turnbuckle and turnbuckle is also one of those words that you probably, there's a small chance that you don't know what that is. So look up what a turnbuckle is, but it's a way to kind of tighten things down if you don't already know. And we'll just kind of spin the turnbuckle and tighten and tighten and tighten this element and this element. And as we tighten it, you can see that we're pushing up this strut up and supporting it mid-span. So then our maximum moment is going to be greatly reduced because we no longer have this kind of sagging point midway. Likewise, in this truss right here, this element's in tension, this element's in compression, this one's in compression, and it's gonna span. And this is not totally unlike a gable truss, but the idea is if we're spanning from here to here, then that midpoint right there is going to be propped up by, in this case, we're making like a teepee on top of it, and then we're going to pull up. We're going to use this tension rod. We're going to tighten it with the turnbuckle, or just kind of turn the bolt or the nut over and over again with the washer until it gets tighter and tighter, until it's actually like pulling the midpoint up right there. And so by pulling it up, again, we've reduced the maximum moment that otherwise would have formed in the middle of the span if it was just a simply supported beam. All right, now that brings us to this. So anytime that you see these cables, you know that they're in tension. And anytime you see a structure like this, and this one's nice, I especially like it because it's got kind of a three-dimensional character. I think a lot of times we think of these, you could tell it was designed in model and not in section and not in plan, but in model. And I'm a sucker for anything that's got a focus on the overhead plane and is designed in model. But anyhow, these elements here, they're going to support this point, and there's another point over here, another kind of ridge over here. So those two ridges are going to be supported by this big hammock that's run by taking cables or thin rods and stretching them there. And I think there's also one, you can't really see it here, maybe it's right here, but there's also one that's kind of going this way. So there's this big net essentially of cables or rods that's holding this up, and then these struts here, this and this and this and this, those are holding up this ridge along here. And so is it some extra structural acrobatics that might not have been necessary? Yeah, possibly, I'm not quite sure, hard to know. All right, now this looks like it's a truss. It has kind of the general idea of a truss. It certainly looks a lot like our truss back here. Let's see if we can find it. It looks like this one, but it's not a truss, and it doesn't behave like one either. So what's happening here is there's not really a truss going on. We just have a beam here. We have a beam here, our rafters there, and we have this beam here is called a ridge beam, if it was a roof. And so this ridge beam, then how is it supported? Well, how come it doesn't just flatten out like we talked about, without this kind of bottom cord that normally would have gone here? How come it doesn't just flatten out? And the reason is because in elevation, at the either end of this ridge beam here, in elevation, kind of back here, back there's a wall, and that wall, or maybe a column in that wall, is going to support that end of the ridge beam, and the other end is going to be supported by the end wall on the other side. So then that ridge beam supports all the rafters, and those rafters behave not as elements in a truss, but rather as simply supported beams. All right. Now this was a tricky one. This was really tricky, and frankly is probably a little bit more difficult than what you're likely to find on the exam, but we can run this one out too. Now, what's going to happen, let's kind of run it through. What's going to happen is we have the loads coming from the top. We have the resistance to the loads coming from these piers on the bottom. And so because we have these loads coming from the top, you can see how this element right here is going to be in compression. I can't describe it except for to say you can just see it. I mean, I can describe it. We'll do that. We'll do a version of that in a second. But basically, everything's kind of squishing it down, and you can see it's in compression. So this element right here is in compression. Now, what we said before is if we have a beam and it's in compression, we're going to show it like this, because that's a description of things pushing together on the beam. But in this case, what I'm going to do is I'm going to say, okay, let's see what's happening at the hinge. So the arrows I'm going to write here are different. They're the opposite of what we find in the middle of the beam, because you can see that the force on the hinge is going to be like this. So this beam here is pushing up on this hinge right here, because that beam, that the weight is pushing down, so it's pushing back up on the hinge. Now, Likewise, over here, by the laws of symmetry, this is going to be under compression as well. So again, this one is also going to be pushing up at the hinge. It's also going to be pushing down on this hinge and down on this hinge. And then our next question is, what's going to happen to this beam right here? Well, that beam right there is going to be, well, let's figure it out. This element right here pushing on the hinge, that thing, I'm going to kind of move it out here. That element right there, that element, I'm making it bigger too so we can see it. That element right there, that vector, is pushing up on the hinge, and we can break that down into a vector that looks like this plus a vector that looks like this. So we can break it down into that. And because it's a vector that looks like that, we can see that if this one is pushing, to the right, and this one is likewise pushing to the left, that this element here is in compression. So this one right here is also in compression. Now, likewise, we see at the bottom here, we can kind of tell that these two, whether they're in compression or not, they're going to kind of cancel each other out just because of symmetry. So on the ends, that becomes more important. And again, we have something that looks like this. And we can break that down into something that looks like this and something that looks like this. And because it looks like this, it's pulling apart. It's pulling apart in this plane. And so this is going to be in tension, and this is going to be in tension. Now, when in doubt, the top outside is almost always going to be in compression. And I say almost always because you never know if there's some kind of weird eccentrically loaded like wind force or snow drift or seismic force, or there's something, there's a really heavy chandelier being suspended from one side that makes the whole thing kind of behave weird. But almost always, everything on top is going to be in compression, and everything on the bottom is going to be in tension. Just like we saw kind of, just a version of essentially of this. All right. Now, the middle ones are a bit more difficult, but we see here that this is making the hinge kind of up that way, and this is pulling, well, it's really kind of pushing it up that way, I guess would be a better way to do it. And this is making this hinge push up that way. And so because of that, these are going to be in tension as well. And again, when in doubt, the middle ones are often, they're not always in tension, but we'll just go ahead. If you're totally stuck on an exam and you don't have time and there's something this complex, that's what you would say. But again, I don't really think that NCARB is really interested in this kind of complexity. I think they just want to make sure that you can see the obvious, the easy kind of slam dunks when an element is a gable, or when it's so clearly in compression or tension, or when there's something hanging, or when there needs to be a strut. That's the kind of level that you need to be competent in, and I'm guessing that most of you are. All right. Now, in practice, you can sometimes see, and in this case it's a little hard to see if this is in tension or compression. I think those are probably in tension for all the reasons we just saw, but sometimes very easy. You can see that the thin members that are cables or rods are going to be in tension, you can see this is a great example of a strut in architecture. So that's like a little compressive strut. All struts are compressive that I know of. There's this net, this kind of tensegrity cable net that's pulling everything back, and that's allowing for these struts to support the roof without having to have a giant truss blocking the middle, blocking all up in here. You could imagine there'd be a truss going, but in this case we want to keep this greenhouse. It looks like we want to keep it kind of free of that so we can bring as much light in as possible. Likewise, you've certainly seen these. This is a skylight, but we see them sometimes on vertical elements as well, and it's a series of cables that are themselves kind of acting as hammocks in this case, and the hammock is pushing up on each strut, and the struts are coming out in these spiders, and those are going to support the glazed elements. All right, for next week, this is your question. Again, it'll be emailed to you. If you're not on the email list, email us at firms@amber-book.com. That's firms@amber-book.com. Those of you who are on our emailing list know that we don't really email you a lot. maybe just about the 40 minutes of competence. But generally, I only believe in emailing people if it's going to help them, not if it's going to help me. So we don't take advantage of your name or sell your data, obviously, or anything like that. That's not who we are. So so the question is, what's the area weighted average U value of this roof? So 77% of the roof is opaque with an R value of 26, and 23% of the roof is transparent skylight. So this area right in here is a transparent skylight, and it's got an R value of 2. So we're asking, what is the area weighted average U value of the roof? All right, now I'm going to go through some of the questions from last week. Someone wanted clarification. Public bidding versus private bidding, kind of, is there a difference? I mean, yes and no. Generally, the process is pretty similar. In the case of private bidding, it can be less transparent because if you're the owner, you don't have to be public about anything. You don't have to open everything publicly. You can open it in your office and make your decision. But generally, and if you're the private bidder, you can probably accept late entries if you wanted to. I don't see any reason why you didn't have to. And generally, the public process has to be much more transparent and much more rule-followy. But in both the public and the private bidding, in the design bid build process, which is what NCARB is kind of using as its default when it's asking you questions about professional competence, it's assuming that it's a design bid build process, and it generally gets it consistently gets the best price because you're asking other people to bid on that. It's just not as good maybe for quality, and certainly not as good for flexibility, because once the contract goes out and they pretty much have to build exactly what was drawn, and for anything that they're going to change, they're going to have a change order, and they're often going to fleece the owner at the change order stage. Which brings us to our next question that someone asked last time. Is it a change order if it does not affect money or time? Yes, it could just affect the design and be a change order. So for instance, I took this the other day. It's an underground cistern for a parking lot that's not even that big. So the idea is that the runoff from the parking lot is not going to go right to the stream and cause erosion and cloud up the water and cause all kinds of problems. What we typically require in the last 30 or 40 years, we typically require each site to kind of handle its own runoff. And one way to do that is to use an underground cistern. And sometimes they're like a big tank, but this one is just a series of giant pipes that are, I guess, welded together or somehow sealed together. And this network of giant pipes becomes the underground cistern. And then you can see right here and here is going to be kind of a manhole to go in and maybe clean it out or unclog something. But in these giant pipes, we're going to store water in a big rain event. And then we're going to somewhere downstream have kind of a little faucet or a little valve called a faucet, and we're going to open it just to drip, and it's just going to drip out. So even if there's a big rain and we don't have we don't have soil anymore that's going to absorb it, we have a impervious surface now because it's pavement. And I don't think pervious was a word, but I've since seen pervious be a word. So I think pervious is now a word, meaning non-impervious. But there was no word in the dictionary some years ago when I looked it up called pervious, just impervious. But anyhow, there's going to be an impervious parking lot. It's on a pretty steep slope, and we're going to capture the water in the cistern and kind of leak it out by taking a faucet on the downside end and just tweaking it open just the tiniest bit and just leaving it open to drip out. That way we're going to limit it. Now the reason I show you that is let's say that during construction it is discovered that where this cistern is supposed to be actually winds up being pretty rocky. So it's going to require the contractor to blast out rock to put it. Now, maybe the soil borings didn't show that there was a big old rocky area in there, because maybe they took a soil boring here and one here and one here and one here just by coincidence, and the rock is kind of in between. There's a big old rock in the middle. And so the question is, like, the contractor will say to the architect, is it okay if I move this if I move this over to the right, 10 feet, and you'll check with the civil engineer, or the hydrologist you have on site, on staff, or that you have as a consultant, and they will say, sure, I think that's fine, that shouldn't make any difference at all. So it may be that it makes no difference in cost because it was never planned on blasting out rock, and it may be that it makes no difference in the timetable, in the calendar, because it's not going to take us any longer to dig this giant hole and put these pipes in 10 feet over to the right to avoid the rock, but it's still going to be a change order. So the question is, if it doesn't affect money or time, but it does affect, even if it doesn't affect money and time, if it affects the design, so it's the money, the time, or the design, if any one of those three things are changed, it's not enough just for the contractor to call the architect, say, can I move it over? The architect to call the civil engineer and say, can you move it over? And then the civil engineer says, sure. And then you, the architect, tell the contractor, you can move it over. And the reason for that is because you can imagine, otherwise they would move it all the time, the contractors would. And then you'd call her up and be like, why'd you move it? And the contractor would say, oh, I moved it because you said it was okay. And you'd say, I never said it was okay. Well, then one of your people said it was okay because one of my people called one of your people and they said it was okay. And so to kind of reduce that he said, she said kind of thing, because you can imagine that it may be in their best interest. They may save $20,000 by not having to blast out the rock. So now they've essentially made $20,000 by moving it 10 feet over. There's a huge incentive for the contractor to do something like that just proves to be more expedient or more budget friendly. And you need it in writing from the owner, the architect, and the contractor. Now, the architect is the one who always is going to create the change orders. Like, even though in practice it's all kinds of messy, and sometimes the contractor will say, can I get a change order? Or I filled out a change order form for you. Technically, the architect is the one. The contractor writes, the architect says, this is a problem, can we move it 10 feet over? The architect looks into it, says, yes, you can. The architect then is going to write up a change order and sign it, and hand it to the owner for her to sign it, and hand it to the contractor for him to sign it. And then we have a new design, and that new design may or may not affect money, it often does, and it may or may not affect the calendar, it often does, and it may or may not affect the design, although it often does. So it can be any combination of money, time, or design, and you need a change order if what you're proposing later, or the contractor's proposing later, is different than what was in the contract documents. All right, now, there's one other thing, and we're going to go over that was a short one, so we're going to go over two sets of questions. That was one. The other one really isn't a question, but it's something I've noticed is widespread, and I'd like to correct the record. I think it'll be helpful for the community to correct the record. So there's this many of you know this is the ARE 5.0 reference matrix, and it has a bunch of resources, generally books. Professional Practice, A Guide to Turning Designs into Buildings by Paul Siegel. That's actually a pretty good book, and so forth. And you can see which books are kind of on the list. In the matrix is the parlance we use for which exam. So ostensibly, if you were studying for the PA exam, you would know to look at this one, and know to look at this one, and know to look at this one. And there are a lot of books. I mean, it wouldn't be unusual for PPD or PDD. Maybe there are 30 books on that list, because this is just one page of, 6 or 7 or 8, 5, I don't know. There's many, many pages in the reference matrix. And so I think there's a misunderstanding in the ARE community. And the misunderstanding is as follows. I think folks in the community, many of them, think that 100% of the test items are pulled from the matrix. So in other words, if you were taking CE and you studied this particular book here, and you knew enough of it, then you should pass the test, because 100% of the questions are going to come from that book for that particular exam, or from that book and the others that are on other pages for the CE exam. But in reality, that's not how it works. It's never how it was intended at all. And so it's not, you shouldn't be thinking about it as kind of references or a course textbook, that if you read it, that all the test questions, or almost all the test questions, are going to come from those books. It's not like that at all. The test questions can come from anywhere, and they often come from experiences of the volunteers who make the test questions. So a volunteer will have a situation where, I don't know, there's an argument between the civil engineer and the architect about where utility is going to go, and the architect says, I volunteered at NCARB, I'm going to make a test question out of this argument because it's kind of interesting. Now, this drives NCARB crazy, because NCARB doesn't want architects to volunteers who are architects to make questions about things that they don't know or didn't know until they looked it up, because they themselves are architects. And so NCARB wants to say, look, you yourself are an architect, and you yourself didn't know the answer to that question until it came up in a project. So we're not going to ask the wannabe architects, the emerging professionals, we're not going to ask them a question that you as a licensed architect didn't know. We're going to try to avoid that. So generally they try to avoid that. But in reality, it's not the kind of thing where these are textbooks. In fact, it's quite the opposite. You're getting it all wrong if you're thinking this way. What's happening is the questions on any exam can come from any source at all. But NCARB maintains a library, and that library has a bunch of books, actually including my book, my Architectural Acoustics Illustrated book. When I took the exam, there were 2 for sure, and I think a 3rd pretty sure, questions that I'm almost positive that they ripped right out of my book, because it was the wording that I had in my book verbatim, and I was really proud. But my book's not on the matrix, and so there are lots of books that they can, but it is in the library, in NCARB's library. I know that, they told me that. So the content can come from anywhere, any book, any source, any experience that an architect has. But because the NCARB library has a bunch of books, what they've done for us is they've said, okay, these are the books that questions are most likely, or these are the most popular books. So it's really kind of a transparency play. They're trying to be transparent about the types of books and resources that their test item makers, they call them test items, not questions, but their test item makers are pulling from most often. But that does not by any stretch mean that you should read all these books, nor does it mean that if you read all these books you'll get it right, nor does it mean that you deserve to get it all right if you read all the books. So frankly, that's where the Amber book comes in. I read all the books, and so I have distilled everything down into a format that is kind of useful and kind of fun, and is really comprehensive for all the exams. Now, one of the big differences between ARE 4.0 and ARE 5.0 is NCARB has moved up Bloom's taxonomy. And for those who don't know, Bloom's taxonomy is like the lowest level of learning is remembering, and the highest level of learning is creating. And in between, we have understanding, applying, analyze, evaluate. So one of the things they've done in ARE 5.0 is they've pretty much taken the same bank of 11,000 questions that were in ARE 4.0, and they've rolled them over to ARE 5.0, only they have tried to eliminate most of the remember ones where you have to memorize a word, and most of the questions now they try to put in this apply, understand area, or the evaluate and analyze area. And so as you move up as you move up Bloom's taxonomy to the evaluate, analyze type of questions, you are very unlikely to see kind of a regurgitation of what's in the book. You're much more likely to see a scenario where they say, okay, You're the architect, you have a wall, it's 65 feet long, it's 10 feet high, it's made of concrete block, it weighs this much, it has this kind of rain load on it, whatever. So it's much more likely to be a scenario that's going to come in. And so in response to this kind of misunderstanding, I wanted to make sure that I had it right. So I wrote to Jared Zern, who's NCARB's vice president, and I said, do I have this right, that the matrix is just about making transparent the most common sources, but it's not about like a comprehensive list of all the places where people are coming from? And this is what he wrote me back. He said, item writers can use a lot of resources, including personal experience supported by others, as a rationale for an appropriate ARE question. As I'm sure you know, reading all the books isn't going to guarantee success on the ARE. Candidates need to translate the knowledge they have into appropriate decision-making, parenthesis, especially for objectives identified as analyze and evaluate.
Hello, Michael.
Hello.
Can you hear?
I can.
How you doing? My name is Giovanni. I've already sat for 5 of the 6 exams.
Okay.
And one recurrent issue that I've been asking myself is, there's a lot of questions that talk about programming and locate your chillers in this floor or the lab in this floor, and move things around within a building. And I've been practicing for about 20 years, and there's different ways to skin the cat, right? There's multiple options. Is NCARB at any point considering different options to resolve these questions, or is just one answer that is acceptable?
There's just one answer that they consider to be the best answer. And in general, you kind of want to understand what they're asking. So if the issue is efficiency in duct layout, then there may be one answer. If you can tell the issue is smart urbanism, there may be another correct answer. If you can tell that the issue is noise isolation from the people walking above, then there's a third correct answer. So I'm not a big fan of trying to divine exactly what they're asking, but in those cases in particular, they're asking something very specific. So probably buried in the answer or buried in the information they're giving you, they're letting you know what the priority is. So the priority is shading. And so you realize that the floor with all the windows is, you want that lower so the trees that are on site can shade that floor, and the other floors don't have as many windows, so they can be higher. And so it may say, like, from a heat loss point of view, what floor should this be on? Or maybe it'll have in the drawing, it'll say, window needs shade or something like that. Or they'll say from an energy perspective in using air conditioning. So it's incumbent upon you to kind of think about what they're asking in those situations. But they're tricky. Those are tricky questions, and often you can probably, especially if you don't realize they're asking about shading, you can make a reasonable assumption based on acoustics or efficiency of duct layout or urban principles that it should be something else on the bottom floor that allows for more eyes on the street, or allows for more revenue being generated by leasing out commercial space for retail, or whatever the other issues are. But once you kind of sit back and look what they're asking, it's usually one that kind of stands out as pretty obvious.
Thank you, Michael. I appreciate that, and I appreciate your videos a lot. You did a fantastic job, and I use them every day. So
man, you made my day. You made my day. So, and I appreciate you guys listening to my voice when you must be so sick of it after hearing me so much. I had someone write me the other day. Her two kids are using. We have another. Some of you guys know this. Many of you don't. But I also made an SAT and ACT prep that uses the same principle, that everyone's a visual learner and that we can animate things that we would otherwise have to learn statically. It's called the Olive Book, and she's using the Amber Book, and her two kids are using the Olive Book. And she said my voice is just around her house all together all the time. And nobody likes their own voice, so I expressed my condolences and my sympathies to her and her family. But she said that, actually she kind of admitted they're a little sick of my voice, but they seem to be happy with the content. Anybody else?
Do you have a training course?
ACT and SAT, yeah, it's called the Olive Book.
Olive book. Okay, that's interesting. I'll look for it. Olive book. Thank you.
Sure. Anybody else? All right. Well, thank you everybody for joining me on my birthday, and I will talk to you guys next week. Remember, next week it's at 6 p.m. at a different Eastern at a different address, not the time we're meeting now, but 6 p.m. from here on out. And you know what? We're going to send you out a calendar, kind of a calendar link as well, so that it can show up on your calendar as recurring. But if you would, just take a minute now and go ahead and put it on. Because I think what a lot of people do is they think, oh, okay, I'm gonna attend it live, and they think, well, I'm a little busy now. I'll check it out later on YouTube, which you're welcome to do. But I think it's better to attend it live, especially because I'm going to be doing more and more of these kind of interactive ones where I send you guys into breakout rooms to answer amongst yourselves, and I think you'll get more out of that. So set it in your calendar now to repeat at 6 p.m. At this address, at this Zoom address. You could take a screenshot of it, and then I'll see you guys there next week at 6.